Welcome to the 5th lecture in our course on quantum mechanics. In the last lecture, we saw and explored the strange quantum idea of wave-particle duality, an idea that applies both to light and to matter. Everything has both wave properties and particle properties. Light has light waves. Also, light is made of photons. Electrons are particles, but they also have wave properties, frequency, wavelength, constructive and destructive interference. And there are two connections between wave and particle ideas. The first connection is encompassed in the Planck-de Broglie relations, formulas that connect the particle energy and momentum with the wave frequency and wavelength. The second connection is the Born rule, that the wave intensity determines the particle probability, that the waves in quantum mechanics are waves of probability. This time, we're going to see how the wave characteristics of matter explain the structure of atoms. What do we mean, the structure of atoms? Well, of course, to the Greeks, there was no real question about the structure of atoms. The very word atom comes from a Greek word meaning not divisible. Atoms are not made of parts. Plato believed that atoms of different kinds had different shapes, but basically Greeks believed that atoms had no parts, no internal structure. But by the end of the 19th century, it became clear that the true atoms of nature did have an internal structure. And so atomic structure, how those parts were arranged, was a serious problem in the early 1900s. By 1900, it was clear that atoms were made of smaller pieces, like electrons. The question is, what's the internal arrangement of the atom? Well, of course, atoms are thousands of times too small for an ordinary microscope to see them. So it's kind of hard to figure out what their internal arrangement is. There were lots of theories. There was one theory which basically an atom was like a blueberry muffin, and the electrons were like the blueberries stuck in the muffin. That was one theory. But then along came Ernest Rutherford. Ernest Rutherford was a New Zealander. He was a physicist at this time working at the University of Manchester. And Rutherford was one of the greatest experimental physicists of all time. At least half a dozen Nobel Prizes were won by Rutherford or by his students and collaborators at his lab in Manchester. By 1909, the time when we join Rutherford in the story, he's already won his Nobel Prize in 1908 for his work on radioactivity. So what Rutherford does is he directs Hans Geiger, his assistant, the Geiger of Geiger counters, and Ernest Marsden, who was a graduate student, to do a particular experiment. He said, I want you to take fast-moving particles from radioactive materials, the particles emitted by radioactive material, and I want you to shoot those particles at a thin gold foil. And I want you to see how those particles scatter. Some of the particles will go barging on through the gold foil, but some of them may be deflected a little bit. We want to see how many are deflected at what angles, how many go out at what angles. And so Geiger and Marsden go into the lab, they very carefully do this experiment, and they come back to Rutherford and they said, we see some of the particles being scattered at very large angles. In fact, some of the particles bounce off of the gold foil and come back. And this is a very surprising result. In fact, Rutherford later said it was the most astonishing thing that had ever happened to him in his life. He said it was as if you'd taken a 16-inch artillery shell, fired it at some tissue paper, and had it bounce back at you. That's maybe an exaggeration, but it is something like shooting a bullet at a muffin and having the bullet bounce off. So Rutherford realizes that his experiment has revealed something about the inner structure of the atom. And Rutherford is able to use his experimental data to create a model of the inside of an atom. And this is the solar system model of the atom. In the solar system model, most of the mass of the atom lies in a heavy central nucleus, which is positively charged, which acts as the sun of our tiny solar system. And this heavy central nucleus, this very dense concentration of mass, that's the thing that Rutherford's particles are bouncing off of. And in fact, Rutherford's experimental data allow him to determine the size of this nucleus. And it's about 100,000 times smaller than an atom. So almost all of the mass is in a very tiny part of the center of the atom. Now around the nucleus, you have the electrons, which have very low mass and are negatively charged, orbiting kind of like planets orbit around the sun. The solar system model of the atom. Now, Rutherford's scattering experiment is one of the great experiments in the history of physics. In fact, my dog was called Rutherford Scattering. It seemed to be a good name for a Springer Spaniel. And but the model of the atom that the experiment leads us to is a terrible puzzle. Why? Well, if you think just in terms of classical physics, the orbiting electrons in the atom should radiate electromagnetic waves. When you take an electrically charged particle and you wave it around in a circle, you produce electromagnetic waves. And so if the atoms are continually emitting electromagnetic waves, they should lose energy. And if the electrons lose energy, their orbits should spiral inward toward the nucleus. So the atom should collapse inward. It should implode. How long should it take? Less than a microsecond. So if Rutherford's model is right, then every atom in the universe should implode in a microsecond. But they don't implode. So the question becomes, what is it that keeps the atoms from imploding? So along comes the second hero of our lecture, the Danish physicist Niels Bohr, who in 1913, as a young postdoctoral student, comes to work in Rutherford's lab. Now, Bohr is a theoretical physicist, like me. He's a physicist that works with chalkboards and mathematics. And Rutherford, the great experimentalist, usually doesn't like theorists. But he makes an exception for Bohr. I believe he made an exception for Bohr because Bohr was also an excellent soccer player. In fact, Bohr's brother Harold was on the Danish national team, as well as being a mathematician. So Bohr comes to work for Rutherford, and he tries to use the new quantum ideas of Planck and Einstein, these revolutionary ideas that are sort of in the air, to explain atomic structure, to explain how Rutherford's solar system model could be right. And so this became the Bohr model. So let's talk about the Bohr model of the atom. In the Bohr model of the atom, only discrete orbits are possible. Only certain orbits are possible for the electron. The electron can orbit in this orbit, it can orbit in this orbit, but not in between. Only certain orbits are possible. The orbits are discrete. It's a quantum effect. And Bohr also said, when an electron jumps from one orbit to another orbit, the electron absorbs or emits a photon. So, let's think about this in a more abstract picture. The different Bohr orbits are the rungs of a kind of ladder. But the rungs are at different heights, not in space, but in energy. The lowest rungs are low energy orbits. They correspond to the small orbits that are around the atom. And the higher rungs correspond to larger orbits. So there are only certain rungs on the energy ladder that the electron can occupy. These are the energy levels of the atom. And so when an electron absorbs a photon, when an electron in an atom absorbs a photon, it jumps to a higher rung on the energy ladder. And if an electron emits a photon, it loses energy, and it jumps to a lower rung on the energy ladder. And what determines the energy of the photon that is absorbed or emitted? The spacing between the rungs on the ladder. Now, several things going on here. One is that there's a bottom rung. There's an innermost orbit. And if the electron is in the bottom rung, if it's in the innermost orbit, then it can't lose any more energy. It's in its lowest possible energy. So there's a stable inner orbit. And this is why atoms can be stable, because there's a rung below which there are no other rungs. There's a bottom to the ladder. So Bohr applied quantum ideas very cleverly, and he was actually able to predict the pattern of energy levels in the hydrogen atom. Why the hydrogen atom? Well, hydrogen is the simplest type of atom. It's only got a nucleus consisting of a proton and one electron. So you always turn to the simplest case first when you're trying out something new. And Bohr was able to exactly predict the energy levels in hydrogen from quantum ideas. And that energy level pattern corresponds to a set of spaces between the rungs, a set of possible photon energies that can be emitted by hydrogen. So if the electron jumps down from energy level number 3 to energy level number 2, then the photon comes out with red light. It's a red photon. It corresponds to red light. If it jumps from number 4 to number 2, it comes out green. If it jumps from 5 to number 2, it comes out kind of a deep blue. And indeed, when we look at the light that is emitted by hot hydrogen atoms, we find that we get some red light, we get some green light, we get some deep blue light. So what Bohr is able to do is explain the emission spectrum of hydrogen. And that's a tremendous advance. Just from quantum ideas, he's able to explain the particular pattern of wavelengths that hot hydrogen gas emits. Now, Bohr was very ambitious. Bohr wanted to explain not just the frequencies of light emitted by hydrogen, he wanted to explain the frequencies of light emitted by all kinds of atoms, by hydrogen and helium and lithium and carbon and iron and so on. And so he worked and worked and was very hard, and Rutherford said, "This is a brilliant idea, Bohr, you should publish this." And Bohr said, "Oh, well, I'd really like to work out the spectral patterns for all the elements." And Rutherford said, "Don't worry, if you can explain hydrogen and helium, you can just let everybody else believe the rest. They'll believe everything." Hydrogen and helium being the two simplest elements. Well, Bohr was in fact not able to explain even the spectrum of helium, but hydrogen he was able to explain quite well. So this is an amazing discovery, an amazing insight into the structure of atoms. Rutherford's solar system model works. It works because the orbits are discrete, and there's a lowest one. It works, but like a lot of early quantum theory, it's a bit fishy. I mean, there were a few quantum ideas that Bohr sort of brilliantly worked into his analysis, but most of his analysis relied on old-fashioned classical ideas. In other words, Bohr was being quite a bit inconsistent in his way of reasoning. Sometimes he would reason this way, sometimes he would reason that way. And so Bohr's model, although brilliant and tremendously influential, and in some respects exactly right, in other respects wasn't really well understood until de Broglie came along more than a decade later with his electron waves. Now, here's the story that de Broglie told. De Broglie said the Bohr orbits are explained by standing wave patterns. Now, what's a standing wave? Well, if we have a wave system and we confine it in space, then we find that only certain wave patterns are even possible. Only certain wave patterns, or perhaps combinations of those. And so the simplest example that everyone talks about is a stretched piano wire. A piano wire is fixed at both ends, but in the middle it's free to vibrate. And when you look at how the piano wire vibrates, the wave pattern of the piano wire must exactly fit between the two ends of the piano wire, because the piano wire is clamped at the two ends and can't vibrate there. So you find that half of a wavelength can fit between the two ends, or one full wavelength, or 3/2 of a wavelength, and so on. Only certain standing wave patterns are possible, or combinations of those. And because only certain wavelengths are possible for the vibrations of the stretched wire, that means that only certain vibration frequencies are possible, because frequency and wavelength are related. And this is why a piano wire makes a definite musical note when struck. When you hit a piano wire, it can only vibrate at certain frequencies. In fact, there's a fundamental frequency it can vibrate at, and it can vibrate at twice that frequency or 3 times that frequency, and so on. And that means that when you strike a piano string, it makes a definite musical note. If you just knock on a door, it doesn't make a very definite musical note because it can vibrate lots of different ways, but the stretched wire can only vibrate in certain ways. It turns out, in fact, that all musical instruments work in exactly this way. That stringed instruments work because the vibration of a wire fixed at both ends can only have certain frequencies involved. A piano, or a guitar, or a violin makes pure musical tones because we have a stretched wire with fixed endpoints, can only vibrate at certain frequencies. And the same thing is true for wind instruments. An organ pipe, or a clarinet, or a trumpet work because we confine air to a tube. And in that confined space, only certain sound frequencies are possible. And so when we cause the air to vibrate in the tube, and maybe we twist the tube up like in a trumpet, when we cause the air to vibrate in the tube, we only get certain discrete frequencies, we only get certain musical tones. So almost all musical instruments work in this way. So the electron in an atom, according to Bohr, or actually according to de Broglie's picture of Bohr's model, an electron in an atom is like the string of a violin. It can only vibrate in certain ways, it can only have certain standing wave patterns, it can only have certain frequencies, and it only has certain frequencies, therefore it only has certain energies. Only certain de Broglie wave patterns fit around the atom. Only certain wavelengths and frequencies are possible. And that means that only certain electron energies are possible. So the standing wave patterns around the nucleus are exactly Bohr's orbits. So de Broglie proposes his ideas in 1924. And it really triggers an immense creative burst in the physics community. And just 2 years later, the Austrian physicist Erwin Schrödinger provides a detailed mathematical description of de Broglie's waves. Schrödinger writes down an equation that describes how quantum waves, how the waves of electrons, move and spread out in space. This mathematical equation is exactly the tool that's needed for working out the details of atomic structure, not just for hydrogen, which Bohr had explained fairly well, but also for atoms having many electrons. So I want to show you here on the screen the famous Schrödinger equation. I'm going to provide it here for aesthetic value only. You see it's kind of abstruse. There are lots of parts to it. It actually, in its bones, turns out to be simply an equation about energy, but that will take us a bit too far afield to explain that. The key thing I want to explain about the Schrödinger equation is this symbol that appears in every term of the equation, the symbol represented by the Greek letter psi, the Greek letter that looks like a little trident. The Greek letter psi. What is psi? Psi is a mathematical object that physicists call the wave function. It's the mathematical object that corresponds to de Broglie waves. It describes de Broglie's wave. And the wave intensity, which is given by psi squared, the wave intensity at any point in space, tells us the probability that the particle we're talking about is found at that location. So the wave function psi, whose behavior is governed by the Schrödinger equation, is the mathematical object that corresponds to de Broglie's waves. It's the mathematical presentation of de Broglie's ideas. So in order to find out what happens in quantum mechanics, all we need to do is solve the Schrödinger equation. That's all we have to do, and we can figure out what's going to happen to atoms and molecules and electrons. Of course, that's the trick, isn't it? Solving the Schrödinger equation can be really, really hard. It's a complicated equation. It can be really hard, especially when you have many particles involved. In an atom like hydrogen, you have one electron moving around the nucleus. But in an atom of carbon, you have 6 electrons, all moving around the nucleus and also exerting forces on each other. The Schrödinger equation becomes extremely complicated. And in a heavy atom, a uranium atom, there are 92 electrons moving around the nucleus and exerting forces all on each other. It's a tremendously difficult problem. Physics students, when they learn quantum mechanics, spend something like 90% of their time in their courses learning to solve the Schrödinger equation. They learn to solve it in this situation, in that situation, the other situation. They learn this mathematical technique for solving it, that mathematical technique for solving it, this way to approximate it. They learn a whole bag of tricks. And some physicists, quantum physicists, spend 90% of their time and lots of computing power trying to solve the Schrödinger equation in complicated situations, like the situations for many electron atoms. So you might imagine that 90% of our business for the rest of the course will be solving Schrödinger's equation. Luckily, we don't have to do that. We can skip it. It's not that it's not an important part of the everyday quantum mechanics that a physicist uses, but we have more important things on our mind. We have more important business to attend to. We want to get at the ideas instead of the mathematical drudgery. Let's just summarize the general result then, what you get when you solve the Schrödinger equation. What you get when you solve the Schrödinger equation for electrons and atoms is you get standing wave patterns for the electrons. And each standing wave pattern corresponds to a different energy level in Bohr's energy level ladder. And the wave patterns are changed. You jump from one energy level to another when you emit or absorb a photon of light. It's a beautiful picture, and it works in detail to explain all kinds of things. So what kinds of things can you explain? Well, you can explain the energy levels in atoms and molecules. You can explain what energies are possible for the electrons in those systems. You can also explain the emission and absorption of light. You can explain why a particular atom or molecule absorbs or emits the frequencies of light that it absorbs or emits. And that's pretty amazing. That's pretty astonishing. But you can do even better. You can figure out not just the photon energies, and therefore the colors of the light, but also the probabilities of making certain jumps. When you look at the light coming from, say, hot hydrogen gas, you see all these different colors, all these different frequencies of light. But you also notice that some frequencies of light are more likely to be emitted than others. Some of the frequencies are brighter than others. Some of them have more photons. The Bohr model could never explain this. The Bohr model really doesn't have enough detail in it to explain why a jump from one orbit to another might be more or less likely than another jump. But Schrödinger's equation is a detailed enough picture. It allows us to calculate the probabilities of jumps, and so it allows us to calculate not only the frequencies of the light that comes out of the atoms, but also the intensities of the different frequencies. The Schrödinger equation also tells us about how atoms and their energy levels are affected by outside influences. So, for example, you might imagine we put an atom in an electric field, and an electric field has the property that it will push the nucleus one way and it'll pull the electrons the other way. It'll stretch the atom a little bit. Well, when you stretch the atom, how does that affect the energy levels in the atom? That's something called the Stark effect. Quantum mechanics accounts for it beautifully. And also, you might imagine that you put the atom in a strong magnetic field, and that kind of twists the atom in a certain way. It makes it slightly more favorable for the electrons to go one way rather than the other. And so, how does that affect the energy levels of the atom? Something called the Zeeman effect. Quantum mechanics explains that too. The Schrödinger equation is able to explain all of these things. So we've got an amazing story going on here. We've got the idea of wave-particle duality, which was first glimpsed by Planck and Einstein at the very beginning of the 20th century. And that idea is extended by de Broglie to cover not just light, but matter. And the idea is also interpreted by Born, who tells us that the waves corresponding to an electron are waves of probability. And this explains Bohr's kind of strange theory of the quantum atomic orbits. It says that you only have discrete orbits because you only have certain discrete standing wave patterns for the electron waves about the atom. And in the hands of Schrödinger, the idea becomes a sophisticated mathematical theory that explains the details of atomic structure and molecular structure and all kinds of experiments. So, quantum theory tells us that the physical world has an unexpected discreteness and also an unexpected unpredictability. And the quantum wave is about both. The quantum wave is about both. Only discrete standing wave patterns in the atom, but the waves themselves are waves of probability. So, how does that work out? Where does that lead? Next time, we're going to go on and talk about the beautiful insight of Werner Heisenberg. He said that the randomness of quantum mechanics sets a fundamental limit to the definiteness of the microscopic world. That wave-particle duality implies that the precision of our knowledge of the microscopic world is limited in a fundamental way. So Heisenberg formulates the famous uncertainty principle. And talking about the uncertainty principle will be our business in the next lecture, and I'll see you then.